I'm just to start with, I'm super excited to be chatting with you guys, and to make this sort of interactive, I'll take longer than usual pauses, or at least I'll try to. This is also an exercise for me to do this. And feel free to sort of ask questions, or I think there is a raise hand button, or feel free to unmute yourself. I think whatever feels more natural. So let's get started. Of course, I like to start with this cheeky video because this is something that I really find motivating. This is how I got started in robotics. Of course, this is from the classic cartoons, Rosie. It's very old. I don't know how many of you may even sort of like recognize this robot, if at all. But the big picture idea is motivating a lot of robotics researchers, I would argue, is this promise that science fiction has made to us to provide what you would call out-of-the-box autonomy. It just works. And this is something that that is actually surprisingly challenging. To actually get there, we study algorithmic methods to enable efficient robot learning, particularly in manipulation. And the idea really is to build autonomous systems that can operate in unstructured, open-world environment. And only then would you be able to get something closer to this idea of out-of-the-box autonomy. And in these settings, you don't just want to do one task. If I were to buy a home robot, I would want it to work for vacuuming, cleaning, cooking, laundry, and sort of a variety of these tasks that need to be done, and not just a variety of these tasks, they actually need to be done in a variety of scenarios. So maybe you trained with these sort of like clean studio environments, but they need to work with a variety of new scenes, new tools, and often, if you realize, in more complex environments. So for example, temporal horizon actually may be much longer than you can train for. So the kind of reasoning that you need to do needs to be valid for much longer. Now, the idea really drives the vision of building these robotic companions. And the way I really think about this is not really replacing humans, but really augmenting and enriching humans in both physical and cognitive sense. Now, that said, one could argue that our fascination with robots, particularly kitchen assistants, is as old as AI itself. This is a video of a robot doing kitchen assistance in 1968. Just to give you a sense of how old this is, 1956 was the first time we coined the term AI. 1961 was when we actually had the robot built, and 1968 was when these concepts started appearing. And the idea really is that the robot does all the work and makes you breakfast, pours coffee, and does everything that we really wanted to do. An interesting thing is, what I find is interesting is, let's cut to 2020. This is a video that Sony showed this year at CES. And the remarkable thing is, it was a concept video 50 years ago, and it is a concept video even today. In reality, the challenge of robotics is much more sobering. When you put real robots in these sort of realistic environments, the world is a bit more challenging. It turns out that real perception in real robotics is actually very hard. So what gives? What is going on? What is the difference between what we envisioned 50, 60 years ago and what we have today? And my argument is that it is the lack of algorithmic generalization to unstructured scenarios. And this sort of lack really is what I would argue very common to all applications of robotics. I've given you examples of the kitchen because, of course, a kitchen is a much more relatable example, but the same lack of generalization happens in manufacturing, retail, personal and service robotics, and healthcare. And the solution that I propose to building such models which can generalize is to provide learning algorithms with structured inductive biases and priors. I argue that the solution would be composed of two stages. One, the system needs to be able to take in data in a natural form. So you should be able to do imitation learning from demonstration, where the demonstration itself can come in a variety of mechanisms, let's say teleoperation, videos, or language. Then the system needs to learn to do these tasks, at least in the same environment. And then the other set of algorithms that we need are generalization, how we can take these learned policies to newer environments in new task variations, and how we can learn from what you would call self-practice. But the argument that imitation is really not that easy. Imitation happens at a variety of, let's say, scales. So let's assume you have a mechanism to provide the data. In this case, there's a lady that is teaching, I don't know, how to collect leaves in your garden. Then a 2-year-old can actually look at the lady and try to just copy the motions. Sometimes this can be just think of motion primitives. So perhaps the robot will be able to get the motions right, but looking at just this data at the level of control, you may not actually get it. You may not actually get the task. As you grow older, you get the sense of what needs to happen, and you start doing skill sequencing. So you can actually do planning with this data set, but now, but even that may not be sufficient. And often, even when you grow older, you might understand that there is a notion of the task's purpose that needs to be achieved. So there's a notion of perception where if you understand the purpose, you can actually do the task in a manner that is completely different from what was shown earlier. So what I'll describe today is the idea of learning in robotics is really across all 3 stages of hierarchy here, where control, planning, and perception are intertwined, and intertwined even more so with data, with current data-driven learning methods. And the ideas that I worked on today are applied broadly with applications from home robots, logistics, and healthcare. But today we'll try to focus on home robotics applications. And what I'll do today is describe pieces of recent work in all 4 of these areas, and then give you a broader structure of how I believe, or what sort of open problems I believe need to be solved in all 4 of these areas. So let's start with control. What do we want out of a control algorithm that is fairly general? I would argue one of the things that we would want out of single control algorithm is, can we get a single algorithm or a single algorithmic framework that can learn a diversity of tasks? We can pick diversity of tasks to be vacuuming, sweeping, cooking, or all sorts of things that we would want to do in a home. And even more than that, we want to be able to do this in a manner that is closed loop, in a sense of Visuo-Motor, sort of sensory motor learning, where we don't have to build domain-specific perception modules. So let's consider the task of cleaning. Maybe you need to wipe a radio, or not many people are wiping radios these days, but the idea of surface wiping is a very core common task that appears in a variety of domains, where whether you are cleaning a whiteboard or a surface tabletop. But the interesting thing is that writing a controller for this one particular task can be easy, but it's the generalization that is harder. So the generalization can be, maybe the stains are harder, so you need to push harder, or the surfaces are glass, so you don't want to push too hard, otherwise you'll break the glass itself. So how do we do something like this? So one approach to doing something like this can be said, we will use something that is deep learning end-to-end model. We put in an image and out comes an action, and voila, we are done. But then, as we have known, deep learning can do a variety of interesting and I would say even impressive tasks, where model of the environment is not known, the state of the world is actually an image, and you're operating essentially in a partially observable setting, or at least where the perception is not domain dependent. But the sad part is that these methods are actually very, very sample efficient. It can take days, if not weeks, to do these things. And for every new task, you have to start from scratch completely. Two, in these kind of methods, end-to-end methods, the robot itself, even though it is given, we are learning this model again and again and again for every task. And finally, even if we are able to learn with these sort of reinforcement learning models, the robustness across training and test distributions is actually fairly low. Now, on the contrary, we could argue that we can build a solution for this problem with the compliant controller, or something like a task-based controller. And one of those examples can be operational spaces. Now, how do we do this? We write down the model of the robot. We have some example of how the system works, the kinematics and the dynamics of the system. But the problem in these kind of setups is, for this particular task, I have to now also write down the model of the task. So this task can have, let's say, multi-stage setup where you have to go to the table. Then the gains on the arm may change when you actually make contact, and when you're actually wiping, the gains may be different altogether. And two, if you are building, let's say, a state machine with this system, you will have to define some sort of task dependent or domain dependent perception module. So you'll have to figure out where the table is, or what are you looking for to begin with. Now, the idea that this line of work had was, can we build a system which would have best of both worlds, where we are not as inefficient as RL, yet we don't have to do domain-specific perception design. So one way to think about this is, let's start to think about the policy learning problem in a decomposed manner, or in a structured manner, that instead of learning policy directly on the observations, you're learning a policy on images, but the output of the policy is not exactly torts. You can actually operate in task spaces. Now, how do we do this? One way to think about this is, we can ask the policy to do the hard things in task spaces that is done in a manner that is robot independent. So you can make the output of the policy in task spaces to be position and velocity, but also the impedance controls. So the impedance basically decides where you need to be stiff, while where you need to be, let's say, dynamically moving to be able to achieve the task. A very simple example in wiping would be that you need to be stiff in the tangent plane so that you can maintain forces, but you need to be relaxed or compliant in the along the surface. And this is something that the policy can learn directly rather than fixing. And then we have a mechanism to convert these robot agnostic control parameters into a robot control torque, because we know the robot model. This has the advantages of us being able to supply the robot model. We can still get compliant control. The model is transferable, as I'll show later. But at the same time, we retain all of the advantages that we get from reinforcement learning. The state is images. We don't have to model the environment at all. So just to give you an example, what we'll do is, in this particular case, the task is, the image in the inset is what the robot sees. This is a user's view. The reward model is basically 3 terms, where you want to clean up the table, you want to maintain the contact, and you do not want to push too hard so that you break the robot. And what we'll compare is a variety of action spaces. Action spaces are the output space of your policy. And what we are trying to really show is that you have end effector variable impedance control, where you are basically giving the authority to the policy to control everything, versus, let's say, joint torts. And the main sort of thing to note here is, So the main thing to note here is the performance gap, both in learning, is actually very, very large. So after 1 million steps of training, in the right action space, you have actually solved the task, while if you're doing joint torques, you haven't made a lot of progress at all. And this is image to torque kind of, or image to control kind of setup. The interesting thing is, the choice of correct inductive bias in the model changes sample efficiency. The other thing that you can do, as I said, the model is completely robot agnostic. So you can train with the outer loop of a simulation model and swap it with a real robot. In this particular case, it's the same system. We do not do any sort of sim to real training or randomization in training. Just the ability to swap the dynamics model directly allows us to operate in image-based systems across sim and real. Although there's one thing, that in this particular case, that the input images were converted to binary, so that there is no sim to real gap in input spaces. So moving on. beyond just let's say simple skills that can be learned with reinforcement learning, often it turns out that reinforcement learning, especially with images, is actually very hard. It requires a lot of training, and if you need to do this on a realistic system, uh, it can actually take a lot of effort or data that may not be available to everybody. Not everybody has a robot arm farm. So in that case, the question we were asking is, can we make the system in a manner that is slightly easier? So we don't always train or want to train from scratch, because a lot of the times we know parts of the solution. Uh, Usually in reinforcement learning, we encode this part of the solution explicitly in a dense reward model. But how can we provide all the help we can to the system without explicitly knowing the solution? Uh, what it turns out that is, in structured multi-step tasks, RL actually is much worse than basic heuristics. A simple heuristic that you could, as a robotics engineer, code up in 30 minutes will probably be faster just on wall clock time than actually learning and with an algorithm from scratch. So part of this problem is a lot of the data that you actually collect in a reinforcement learning algorithm is very low signal to noise ratio. It is essentially doing exploration, and random exploration is very slow. On the contrary, even though when we know that the first step in this particular case is fairly obvious, just go to the handle, providing that part of the solution should speed this up, but there is no simple way to provide this input. So what we basically were asking this question: can we guide exploration in a manner without explicit solution is being providing explicit solutions? So let's consider this simple task. The task in this case is, there is a block on the table that needs to be moved to a particular goal. In this case, there's a red point. All of these initial and final positions can change. And then the block can actually be placed farther than the arm can reach. In that case, the system needs to learn either directly go to the block or actually grab this hooking tool and pull the block to the solution. And we can say that we can build in very simple solvers which can be thought of as partial teachers. So maybe grab the hook, or pull, or push. These are easy to code up solutions which do not really capture the full task, but are partial solutions that are easy to specify by a designer without actually designing a full state machine. And the idea is that, can we use these features which are partial and not even complete, or even sort of no mechanism is given to us that how to use these features, for faster agent training and optimal test and performance. So as I said, the teachers can be partial in the sense of they can in principle be sequenced, but it's not necessary they can be sequenced together. Or they can sometimes even be contradictory. You are trying to put together two teachers, which is one of them is grab the tool and the other one is let it go. And then you are basically stuck. So how do we actually use all of the information that we are given, but without structure? This is an open world kind of setup. So what we do is propose this idea of Actor-Critic with teachers, where the environment outputs some sort of state. The state is actually fed into a policy, but also to all of your algorithmic features. These are essentially heuristics that you have put it up. Each of them can actually output some sort of action. Now the question is, at the point of training, which algorithm should you trust? So then we can build a second model of distribution of our belief over each of these policies. Essentially, teachers are fixed policies while you are learning the algorithm. And you can rank these policies. So you can build a critic over all of these policies, which is basically maintaining a belief over how good is your policy with respect to the teachers. Initially, the agent policy might be very bad. Based on the ranking of this Bayesian critic, you actually pick a particular policy to run. That policy gives you an action. And now, because the whole model is doing off-policy learning, even though in the beginning, when you believe that teachers are better than my actor, I can train my actor with this off-policy data. So none of the data goes to waste. All of the data goes to a buffer, which I can learn from. But eventually, as the training progresses, your agent policy becomes better than the teachers. So you can actually improve upon the teachers itself. So a good example, going back to the same task, where we start with 4 teachers, which is grab and hook, position hook, pull and push. So the first test we ran was what happens when you have a single teacher that can do the full task. So first of all, this is more of a sanity check to ensure that nothing we did breaks the model. So if you're just doing a pure RL with no teachers, it's very slow, but RL with a single teacher near optimally, our model would work very similar. But the interesting gains actually appear when you have multiple teachers. So you have to learn to sequence them. So in this case, the blue curve is AC teach, while the yellow curve is Bayesian DDPG. So there's an outer loop, but the inner loop is still complete RL. And no teachers is too slow to actually even compare. In this case, there is a performance gap. And it is even more evident when what happens in this case is the teachers are not complete. So the teachers are, the agent has to learn behavior where the teachers cannot be sequenced into, the agents cannot be just sequenced to a solution. So just to take a moment here, I talked about action representation learning, and I also talked about how weak supervision like heuristics can provide structure to enable efficiency and generalization in learning with reinforcement. Any questions so far?
Yeah, Animesh.
Yes. Hi.
In the previous slide, you said, I think you were cutting off. I didn't quite understand when you said the agent cannot sequence the teachers. Could you elaborate what you mean by that? Thanks.
Absolutely. So think of teachers where these are heuristics, but there is no guarantee that the heuristics can actually complete the task. So you can basically think of it like this, that if the number of heuristics that are provided, there is no solution by simply sequencing the heuristics. There are parts of the solution that are missing. So you provided some parts of the teacher. For example, in this case, you can say that I provided a solution of grabbing the tool, but not actually pushing and pulling with it. Then it still needs to learn the push and pull aspect of it, but the grabbing part should still use the teacher. Not using any teachers is throwing away information on the table.
Got it. Thanks.
Any more questions before we move on? If not, then let's move on to the next stages of the task of planning. So we started with simple skills, which were what you would call primitive skills, but the world world exhibits slightly more interesting sequential skills where you might need to hammer, cut, sweep, or perhaps use tools. So we started to look at a problem, which was this idea of manipulation with tools, but with unknown objects. So think of this simple setup. You are given an arbitrary object and you are asked to do a particular task with it. In one of those cases, a task can be sweeping with the tool, and the other task can be hammering with the tool. Now, if you're trying to do this with an unknown object, a particular pipeline can be, let me grab the tool optimally with where we are optimizing for grasp success, and then I will optimize for the task. But then I would argue that nobody actually grabs the hammer at the center of mass to actually hammer. The task drives the grasp rather than the other way around. So in this particular case, we were asking this question: how can we learn this sort of model of task-driven grasping or task-oriented grasping without explicitly providing solutions? They can also be thought of as affordances, but we are not providing this guidance of affordance. So what we set up as the task is you're given a depth image as input. You are provided a task embedding or a task specification. And the solution that we're looking for is some sort of grasp parameters and grasp output and a policy how to use this grasp in this particular task. So you're trying to do the task with this object, but you have to grasp it in a manner that will complete the task. Now the search space can actually be prohibitively large. So to model this problem, we think about finding the problem of optimal grasp and an optimal policy simultaneously as maximizing some sort of score function. And the score function can be written out as basically probability of success of the task given a pair of object and grasp. Interesting thing to note here is that every time the task succeeds, you can argue that the graph must have been successful, but the other way around is actually not true. This intuition actually allows us to factorize the score function into a graph success model and a task conditioned graph success model. This enables us to write this Q function essentially, or score function, into two separate models where we are predicting how good is the grasp and simultaneously also predicting what is the task success rate given the grasp is successful. And simultaneously, the third model can be a policy gradient that you can train for the policy. So you can have three particular loss functions. One is more run-of-the-mill graph success model. Then you can have a conditional task-oriented model. And finally, a policy model, which can be trained with a policy gradient. Since all of this is fairly sample inefficient, the whole training can be done in simulation, where we generate procedurally about 20,000 tools in a variety of these episodes, and we can create a lot of data in simulation. Now, in terms of inference, at inference time, what happens is we basically run the model with a new object. You generate a lot of grasp candidates, but these grasp candidates are now ranked according to a task-oriented grasp model. Picking the best candidate, now you can run a manipulation policy on this new object. The new object does not need to be known either in category or in shape. So this is an example of qualitative output of the system where these are unseen objects at test time. And in terms of performance, you can think of a very simple baseline where you're grasping any object with the antipodal grasping model and then optimizing for it. Then you can have a task agnostic model where you are basically doing two-stage planning, the optimal grasping and then optimal policy learning, but separately. And then we double the performance when you optimize this jointly. And the same thing actually happens when you change the task from sim to actually doing this on real. So here you see, because the whole training set was completely simulated, all of these objects are obviously out of distribution. And the kind of performance gains are very similar in both sweeping and hammering, where the system learns to pick the right grasp model for the particular task. In this case, each of these hammering and sweeping policies are trained separately. So going forward, we started talking about tool use, but then we started looking at how can we do tool use for slightly longer term sort of reasoning. Let's say multi-step reasoning, where you have to reason about not just the tool, but actually perhaps about the environment and its constraints. So in this simple setup, the idea was we were looking at these sort of animal intelligence problems where you can roll the pin, but the pin should not roll off the table because it needs, let's say, a supporting object, while the Campbell's soup bottle is actually an obstacle, so that needs to get out of the way. So you're doing multi-step task and motion planning simultaneously. And this, of course, needs to generalize with multiple sort of shapes of objects and shapes of tools. So what we are basically asking the question is, can we learn this multi-step reasoning in robotics under physical and semantic constraints simultaneously? So a simple example in this case would be there's a target object that needs to goal position, but the constraint in this setup is that the object needs to stay on the path. So it's not just a simple pushing task, but it has to stay on the path. So a simple solution for this might be along the lines of this sort of green stages where you push along the line. But now suddenly, if I add obstacles, it becomes a harder task because now you have to make discrete decision, which object to push, in what dimension to push is a continuous decision. And then you go back after cleaning the task to going back to pushing the object. So this is essentially a discrete optimization problem where you're picking which object to push, first of all, and then deciding the policy to push it with. Now one could argue that we can build a dynamics model of this environment and solve this with a model-based system where the model can be learned purely in image spaces. This would not be new because many people have done this, it seems. Of late, friends from a variety of places, DeepMind, Google, have built these sort of dynamics models. But the question really is that as the problem becomes a bit more complicated in these kind of systems where pushing is not just greedy, the amount of data required goes up exponentially. And it is not clear, even then, would it work? All of these tasks so far have been sort of simple, greedy pushes. So in that case, what we propose is that to build a hierarchical dynamics model where you are basically building hierarchical abstraction in the action spaces, but without providing explicit hierarchical supervision. So the data is all self-supervised random pushes. So you're not actually telling the system the solution. Now, the two-stage dynamics model can be really thought of as an effect system, which is basically predicting course dynamics for longer terms. So think of going to the airport, planning for 2 different routes. And then a local level motion code, which is basically saying that conditioned on a particular route you're going to take, what is the low level sort of like what is the next turn by turn guidance? So what we do is we basically train a metadynamics model where you are training in these abstract action spaces for longer term dynamics, which enables you to choose the right discrete path. Once this decision is made, you can simultaneously pick what action should be chosen locally, and then you can regularize the model with locally learned dynamics to ensure that the actions that are predicted by the model are valid or dynamically aware. So now what we do is we basically create a lot of task agnostic interaction in this environment where the robot is essentially pushing randomly. You build the model of metadynamics and an action generator conditioned on the metadynamics. Again, to emphasize, both the effect code and the motion code are essentially latent. So you are not providing any supervision for these Q functions. So at sort of test time, what you do is you look at a scene. The scene converts the visual observation into a scene graph model where you have multiple objects. Each object itself is unknown, the shape. Then you put in this sort of scene graph model with object features into the cabin planner, the model, which can output a local action space. The action space is relative position and direction from the end effector. So we talked about this crossing task, but we also looked at 2 other tasks. One is clearing, where the idea is to clear all objects out of a particular region. Other one is basically slotting or insertion, where you have to move a particular object into a particular position while all other objects are distractors. And what we see comparing this sort of hierarchical model is that when you have a particular structured model, the closest, which is a very complicated model in sector, we can get performance gains. But the interesting thing is the performance gains are slightly larger in sparse reward, where you only get sort of success rewards. And of course, you can put this on the real system because the whole thing is trained with depth images. And you can get very similar performances. So the big picture idea is that hierarchical latent space dynamics enables better performance with only sparse reward signal and non-task specific modeling. So just to give you an example, in this case, it needs to first move 2 obstacles, the green chips and 2 chips bags out of this so that it can move the yellow box to the yellow spot. Similarly, in this particular case, it figures out that instead of moving the other objects, it can go around the system. So it does a non-greedy sort of sequence of pushes. In this particular case, it figures out that it can actually open a path by moving the green bag of chips outside and keep pushing this sort of box of raisins into the box. So in both of these cases, what we did was we showed that you can use weak or self-supervision with structured latent variable models because they lead to very good representations that can generalize across these tasks. So in this particular case, what I just showed you, for all 3 tasks, we have the same model trained in the same environment. So you can do a variety of tasks with a single model, because now you have essentially reduced a policy learning problem to a model-based planning problem, and the complexity of the problem is in model learning itself, not the planning part. So before we move on, any questions? If there are no questions, I'll proceed. So the next stage is basically we have looked at tasks that were either single skills or let's say 2-stage sequential skills. But the world actually may be much, much more complicated, maybe cooking or doing laundry or object arrangement, where the actual task or sequence of tasks you need to do is actually a tree, not just two-stage decision making. In this particular case, we were thinking about how we would look at such a problem. How would we do a tree structured problem where we already know reinforcement learning is fairly sample inefficient for simple tasks as it is. It has no hope of working in very, very complex domains. Now, one could argue we can do imitation learning, but imitation learning itself requires data that is segmented a priori, and that segmentation is non-trivial. What we really need is what you would call meta-imitation learning, where the idea is you solve domains rather than particular tasks. So let me explain what I mean by this. Think of a simple Lego world domain where you are basically given pieces of blocks. Each of these blocks can be arranged into a particular permutation. Each permutation can be thought of as one particular task. Now you are given some instructional demos for a particular training set of tasks. You want to be able to do them, but at test time, you will be given one particular final configuration, whether through a video or through one sort of goal image to achieve. And you have to come up with a policy that can do this in a closed loop fashion. Now, other people in last few years have attempted this problem by the name of one-shot imitation learning. But often what happens in these cases is that the input demonstration and the policy are both modeled as a flat sequence. On the contrary, what we really want to do is to enforce that the input and the model can both be compositional. So a very simple way of thinking about this is, how do we do this task? One way of doing this task can actually be just writing a program to do this task. So let's say stack red on blue. But the problem in this case is that you have to write a new program for every new subtask. So the intuition of this sort of line of work was maybe we can reduce the learning problem to a supervised learning problem where we are essentially doing programming. So it's a meta-learning model that takes in some video as input and outputs a conditional policy. The model itself is essentially an LSTM model that takes in current state, some demonstration, some encoding of the video, and the current state of the policy, which is the current program. And the output of the system is the next program or subroutine to pick. And it has to output two things. One, the API function call and the arguments to call the function with. So in this case, pick would be one output and blue would be another output. And the mechanism to train this with is essentially doing explicit loss and compare with the ground truth program. So the training supervision is pairs of demonstration data in a hierarchical program trace. So you're basically giving the system both the low-level actions and the hierarchical actions, and the system can now essentially parse the program and decide how to call subroutines. So we are posing a hierarchical policy learning problem as a program induction problem. So let me sort of like give you intuition. You start by an input video. The policy or the model outputs this sort of intimidating looking policy, but you can really think of this as a very simple setup where the high level policy is block stacking. When the block stacking phase is complete, you call pick and place. The pick and place model will in turn call pick, which will in turn call an executable model at the robot level API, move. And move to is past a block argument, which it can move to, in this case, let's say blue block. Then once this block completes in success, the program counter moves back to pick, where pick moves to the next phase of grasping the object. When the pick completes the pick and it goes back up to pick and place, which moves to the next part of placing the object, and so on and so forth. And then once the pick and place is complete, the pointer moves back to block stacking, and the block stacking can move forward. So this is just an example of one pick and place. We actually ran these tests with where the solution required more than 40 sequences of 40 pick and places. So a simple example of what this enables is now you can provide a demonstration of a particular task in pure VR kind of setup. In this particular case, the important thing to note is the configuration or the permutation of objects. And now looking at this video, you can initialize a policy on the system, which can actually first parse the video into what needs to be done and then come up with a policy to achieve this task. The interesting thing, as I said, this is actually a policy, not just a parser. So it can actually do state conditional corrections. So let's say if the dynamics was stochastic or an adversarial actor existed in the system, you could Now, you will not now continue doing the wrong thing, but actually go back and fix things. So it's not just a simple parser. It results in a closed loop feedback policy. So just to compare quantitatively, what we see on this graph here is basically in the testing domain with state input. So you have explicit block pose. What we see is flat policy barely performs with new tasks. On the contrary, the new task programming policy has very high performance. The same thing can now be done with visual input as well, where you can have a detector plus detector outputs pose, and you have a state-based policy or an end-to-end model. The end-to-end model performs better because you don't have cascading errors and you can do joint optimization. So the big picture takeaway here was that you can have much better generalization than a flat policy because of the compositional structure of the output. You provided a particular kind of inductive bias in the output, and the system can actually be trained with end-to-end visual input. Now, of course, the whole thing wasn't working perfectly. There were many sort of failure modes. The failure modes were basically where the plan could not do long-term planning, or the low-level actions failed without error handling. So what we did was we went back and looked at what was going on in this particular case. What we have is we have inductive bias on the input and the output. So the output is program structured, but the model itself is actually LSTM. It's a black box model. So what we decided is maybe we should open the black box and make it compositional, make it a compositional model prior itself. So the model itself is compositional. How to do that? Instead of thinking about task program, we can now really think of task graphs, where now what the system is doing is not only is it predicting the next step, but it is predicting multiple next steps to go to the goal. So you are basically generating an implicit task graph. Okay, you're generating this sort of like subgraph to complete the task in this setup, and I'll explain how this works. So you can really think of it like this, that you get a demonstration. Demonstration will be a sequence of actions. What the task graph generator is really doing, based on prior that it has seen other examples, not only does it parse the sequence of actions, it also provides other potential ways or other potential pathways from start to goal that will get the task. And this sort of implicit representation enables it to be much more robust. And then you can take this graph and condition a policy onto it. So this task graph executor condition on the implicit graph and the current observation can become the policy itself. Now, how do we create this task graph? So you can think of a task graph where nodes are state and edges are actions. That would be the obvious thing to do. But in any sort of compositional domains, the problem is that the number of states can actually be combinatorial. So creating a graph, even with attention or implicit representations, can be very tricky. So the key idea here was to use a representation that would be conjugate task graphs. In this case, nodes are actions, and actions are limited, by the way, because the number of nodes or the number of API function calls are limited. On the contrary, edges becomes states, and you can have very many edges. So now you can really think of these as for every node, there are preconditions and post-conditions that are implicitly encoded. And now we have a finite representation of the graph. The way to operate on this model is you start with an observation. You basically figure out what was the last action that was done. Provided what action is done, now you pick what are the post conditions, which is basically an edge classifier, which is telling which of the potential post conditions you will end up in. You select an edge, and then you run your node localizer again, so which is the next selected action. So this is how a policy would work for one action selection. Now, of course, all of this can go back, but the big picture idea is there were two things that we updated. One, we started from a compositional model prior, but two, we also completely eliminated hierarchical supervision. So now the training supervision is only a demonstration and low-level actions, which are easy to recover. You don't actually have to specify what the block stacking or the pick and place was. You're basically giving a sequence of move to, grab, open, close in that sense. And now we go back to the same sort of numbers that we saw. We basically compare the NTG numbers with the neural task programming numbers on full state input, and we see basically a marginal input, But the real gain appears when you have this compositional prior with end-to-end model, where we now can see that we can do much, much better and we improve the performance by over 30%. So we have weaker supervision and better generalization in an end-to-end model with the correct inductive bias, both in the model and in the input output. And this idea of sort of block stacking can be applied to any sort of compositional task, let's say clutter object sorting, some sort of particular table cleanup or table setup, or even sequential search and prediction in navigation tasks. So really, the big picture takeaway in this part of the talk is that compositional priors with modular structure enables both generalization, but allow you to actually do much more complicated tasks that simple reinforcement learning will not scale to yet. So now I want to move to the last part of the talk, where we basically want to talk about the data or the data availability. So I don't know if you noted in these kind of tasks, as the task grew more complicated, our data set sizes grew smaller. We started with pure sort of Visuo-Motor tasks where we were basically running millions of examples. Then we went to structured supervision where doing 500,000 to 1 million example was very hard. And then we went into complex structured tasks where the number of tasks we were operating with were of the order of thousands, not millions actually. But to do anything really realistic, procedural execution from videos, we really need to be operating with larger sets of tasks with structured supervision. But how do we get that data? Now, one could argue that imitation learning really has been helping us. But if you look at recent advances in imitation learning, the data sets that they have been using are minuscule, about 25 minutes to 30 minutes of these data sets. And just to compare this, the state of robotics data sets is as of end of 2018 actually, where we had data sets which were measured in hours. So 13 hours was a data set that was collected by folks at CMU, and this was published at Coral 2018. Now comparing this with sizes of data sets that our friends in Vision and NLP are using, we are basically off by 3 to 5 orders of magnitude. So how do we fix this problem? The interesting thing is that both vision and language have access to crowdsourcing where they can get data that is labeled. But in robotics, labeling is much harder because you need to show or demonstrate. Just simple labeling is not sufficient. So we created a system which basically uses commodity hardware instead of VR. So everybody can do it in a crowd, but at the same time provides you with natural 6-stop free space control that a keyboard and a mouse cannot provide. Now the system can be hooked into a simulator to provide very natural data so that you can do both dexterous and cognitive tasks. And at the same time, you can actually do this with full sets of real robots to get complicated real world data. And again, you can do this from anywhere, both in real and simulated environments, depending on how many real robots you have. And then we have ran these systems for both pilot data sets in simulated and real robot data sets to collect over hundreds of hours of data set. And just by comparison, this is about 10 times larger than existing data sets. And we were able to collect them in about 4 to 7 days, depending on whether it was sim or real. The data for sim was collected through true crowdsourcing, where the crowd was actually located in China. And for real data sets, these were Stanford students, but not from the lab. So they did not know how to use the robot or anything about that. They were basically using this ab initio. Now, the big picture question is, okay, we were able to collect the data, but so what? Then what we did was we actually said, let's look at some tasks which are non-trivial for RL and try to do that in sparse reward setting. And what we observed is, if you do sparse reward with about 2 days of training, either of these tasks could not even make progress, even with the distributed setup. On the contrary, as you injected data in the system, we were able to improve performance essentially sort of linearly, and 1,000 was the limit of the data set that we had. So the real takeaway for me was that structured supervision in robotics through scalable crowdsourcing really opens this Pandora's box for us that empowers robot learning for complex tasks. And crowdsourcing really enables us to access this treasure trove of data. So going back, basically I talked about the four stages that I believe that need to be sort of strung together to enable real world robot learning, which involves us thinking about levels of visuo-motor skills at control, then planning to be able to handle perception in a manner that is fairly smart by providing the right inductive biases. And then to actually do all of this, we need a mechanism to do, to get and use data at a scale that makes these data-driven learning methods actually possible. I believe this has also opened a variety of interesting questions in all of four of these domains, starting from adaptation, dynamics learning, perception, and data. And I'll talk about some of them to give you an idea of what sort of things we are working on currently. So for control, I believe not only single task policies, we need to be able to do multitask learning in a few shot settings. So not only we need to do meta learning in the sense of few shot, but we need to be able to do learning without forgetting. So we have been working on these ideas for a while, and one solution that we have come up with is probabilistic context-guided meta learning. It seems to be state of the art for RL. It is currently in review, but we can basically, the big picture idea is that you can learn multiple Q functions with a context, and the context is essentially doing posterior inference about what is the dynamics and what is the task and reward model. So you're basically doing what you would call Bayesian reinforcement learning, where the context is your posterior. Another interesting domain and an open question in imitation learning particularly is almost all of the data that we will get will be anthropomorphic because we have two hands. But often in robotics, why are we limited to two hands? My experience in surgical robotics tells me that actually having more hands may be even better. So you can actually have non-anthropomorphic system. But how do you actually take data from an anthropomorphic system and convert it into a policy for this kind of system? So we are looking at basically learning these systems in a multi-agent reinforcement learning kind of setup, where you are trying to answer questions: what is the best team size? Are two hands better than 3 or 4 or 5? Should all the grippers be the same? Or is there a notion of handedness in the sense of, can you have heterogeneous agents where one of the grippers has a parallel jaw gripper, the other one has a multi-fingered arm? And how would the system work there? Another interesting question in model learning is, so far we have done model learning with latent variables, but really having a richer model with causality embedded in it allows us to do much more. So an end-to-end model was reasonable. People have shown some good results with that. People then went to some more sort of encoder-decoder style models with latent, including our own work that I showed earlier today. But I think what was even more interesting is to actually have a generative model that has the real structure that can generalize to new structures or parameter values. So just to give you a sense, in this particular case, the ground truth is a set of balls that is connected to each other by a latent set of connections, maybe springs, maybe rigid rods. So these are not just balls bouncing around in a closed environment, actually. So the balls are not independent. So you have a spring mass system that you cannot observe. And what we find is that now learning to be able to predict the behavior of this thing requires you to understand what sort of edges may exist, doing inference over those edges, and to do this in a manner that is domain independent. So you actually have to learn some sort of representation scheme. In this case, it's an unsupervised key point setup. And then you have to do an attention mechanism on these key points to build a prediction module where every edge between 2 points can be a nonlinear sort of effect code. So essentially what you're doing is building a causal model, which is the true generative model of the system. So even though, let's say in a test setup, the spring constant changes or the spring doesn't exist anymore, you'll still be able to predict with very few data points. Then, of course, in the sense of perception, we still need to solve the harder problem of dense activity understanding, how to convert an instructional video into even a representation that is executable. So if you see this video, what is the recipe, what is the plan or the structure graph model of this recipe, and how to plan for these sort of low-level actions. Another interesting problem in this case, which I referred to earlier, is basically understanding the grounding, but the grounding should be done by physical interaction. What is it about an object or an object shape or behavior that makes it a hammer or a shovel or a particular tool? And how do you do this learning in a self-supervised manner so that only functional affordances pop out without explicit supervision? And again, grounding is not just for sort of image-based representations. It's also across time. So just saying making eggs is not sufficient, because there are so many ways to make eggs. You have to be able to be specific. If you're not specific, then you have to understand what is happening in the scene to actually do context-driven grounding. Finally, in terms of crowdsourced robotics, we showed that we can actually have utility from a learning perspective of having this large scale data. But now we really want to do this in a manner where we can have a centralized repository where the learning can be done in a never ending fashion, where everybody, whether it's you or me or anybody, our friends at Stanford, they can keep learning and contributing to the same data set, and we can train completely offline in a batch policy manner with this very large data set. And finally, one of the things that we realized in collecting this data is this idea of what I call platoon autonomy. So input will always be limited. It will be limited to one phone, maybe two phones. Almost nobody has two phones though. But how do we actually now control with a 6 DOF input something that is a 12 DOF robot or 18 DOF robot? So we've been working on these ideas where we basically argue that you can actually learn latent spaces where the action is latent. So on the right, what you see is the user is controlling the robot with an end effector control on the left, and on the right, what you see is a latent space where the latent space is essentially controlling, providing the user with only a 2-dimensional input space to control a 6 DOF arm. And what we see is that the user is able to complete the task much faster in a much more smoother manner. So with that, I think I'm also very close to being out of time. I would like to wrap up. And if there's one thing that you take away from this talk, let it be that learning with particular kind of structured inductive biases and priors in the model and in both the input-output structure enables you to achieve the kind of generalization that we hope for our learning models in interactive scenes to be. And I would like to thank a lot of my coworkers and students who worked along with me on these projects for all of the videos that we saw today. And I would like to thank you guys for being such a great audience. Thank you very much.
All right, thank you. I think we have time for some question. Questions, or maybe I'll start with mine and people will start jumping in.
Sure.
Okay, so one thing which I feel is missing in the narrative, and I feel that explicitly, most of the human activities are like, it's like a social behavior or in social environments, like two people doing certain things. And as you started with, it's like a robot doing next to a human being. But all the things that you presented, or most of the people are talking about, is robot in isolation. The data sets that are being collected, the policies that are being learned is about robot in isolation. Now, it's not clear to me as how this notion of social behavior, where a human is there working next to a robot, be encoded in all these policies. Or can these policies be a direct extension of, okay, I learned something in an isolation, can I put a robot next to a human being? I guess the answer is no. But I don't really know as how it can be scaled, or how can we even collect that kind of data.
I think that's actually a very spot on question. The way I think about this is the two sort of lines of work are slightly tangential, or orthogonal rather. Basically, the argument is this: you need to be able to have some sort of skill to be able to offer assistance or sort of a behavior that is smooth in terms of limited communication settings. So when two people work together, there's a common understanding that the other person has some sort of shared prior of either skills or actions, so that in a very low bandwidth communication, you can actually achieve a level of team performance. Now, suddenly, when the robots that we're talking about do not even have very, very basic skills, the trust in the system that where a human has very sort of like dexterous skills, on the contrary, a robot may not even be able to handle spoons properly, will be very hard. So we still need to have these robots get up to a level where there is a mechanism to do basic skills. Now that said, working in shared environments or shared workspaces with humans or other robots is equally important problem that that I'm sure a lot of our colleagues are looking at. It is something that we have not yet reached at the point where we have systems to look at yet. And there's no denying that there is an immense amount of complexity in those setups. People in autonomous driving have already sort of reached at a point where now they can start looking at those problems. But sometimes certain problems are more useful to be looked at in isolation because we do not yet have a working system to really evaluate or do the experiment in shared autonomy kind of workspace. That's something that I know. But of course, I would be very keen to understand what sort of problems emerge when you're operating in a slightly more social setup.
Right. Any questions from other folks?
Hi, Animesh, I have a question. My question is about this idea you touched upon towards the end about structured supervision. I was wondering if there's sort of a middle ground between, for the purpose of specifying a goal or a task, between coding reward functions and giving full-on demonstrations. Because a lot of times the humans might not even be able to give those demonstrations themselves.
Absolutely. I think so. So in particularly the line of work in RoboTurk, we picked tasks where you needed both cognitive and dexterous output. So basically, simple skills are still hard enough to learn in reinforcement learning without you explicitly coding in the solution through reinforcement learning or through reward function modeling. And you still need to do, let's say, reasoning that is, let's say, in a semantic spaces. But as you pointed out, there are explicitly cases where, for example, providing the motion level input may not even be possible. Examples can be, let's say, humanoid robots, where the degrees of freedom is just too high for a human to actually provide motion level input. They can only provide semantic input. In those cases, as I said, we are starting to work in latent action spaces where the latent is what really gives you the separation. So you operate in lower dimensional spaces, whether you're operating multiple fleets of robot or a robot that has very high dimensions, but your action control space is lower. That's one. Two, there is this recent line of work, which is basically also saying that you can do simple reward sketching where the robot itself is doing the learning, but you can actually provide slightly more detailed reward models, which are not explicitly engineered for the task, but are more sort of general 0 to 1 sort of ranking based reward models. Both of those systems seem to work well. Right now, it's not clear which one would be the final solution, but it seems that having these sort of latent structured action spaces will have a solution, will have a sort of space, or will be the part of the puzzle.
Thank you.
Questions? Maybe we can take one last question.
Animesh, I have a question.
Yes.
So in general, like in the vision community, people collect data sets, and it's so easy for other people in the community to use it. But then in robotics, because these data sets are embodied, it's sort of hard for other parts of the community to use it. So do you have any thoughts on how do we collect data sets so that we can share and reuse? Should we just stick to
that was
or?
Oh, no, not at all, actually. So this is the part where I was basically referring to in one of the slides earlier, just before when I was finishing up, that I believe the solution actually requires us to have a mechanism where we can learn in a manner that is offline. Now, what we have found, at least empirically, is that we always believe reinforcement learning was completely an interaction problem because the data sets we were interacting with were very low signal to noise, or the data sets themselves are very small. So if you scale the data to, let's say, millions of examples, often you can do very well completely offline, like no interaction reinforcement learning kind of thing. And that is what we have observed, and others, like particularly DeepMind, which have built equally large systems, also has observed in recent papers as well. So I have a belief that you can actually do very large scale data collection that are reusable. Now, that said, policy evaluation still remains a problem because evaluation still needs to be embodied. The hope is that the data will be at least multitask. So you can do the last mile fine tuning using this data on your task. The same way we do this with ImageNet. Not everybody is solving classification, but we'll still be able to use all of the data that everybody is collecting in a singular repository that we learn off of. And all of this data can be heterogeneous in the sense of whether it's simulated or real. Of course, there are practical systems level challenges of how to mix things. Like, can you do data sets of 2 arms with a single arm? Right now, that doesn't need to, that hasn't been solved, or mobility with manipulation. But at least, let's say, tabletop manipulation, whether it's opening doors or picking objects. So there can be some limit to it. It is not sort of completely open world kind of thing, but still we can get to a regime where we can have data sets that are much, much larger than what we are used to in robotics.
Awesome, yeah, thank you.
All right, I think we should thank the speaker. Thanks, Animesh.
Thank you, everyone. I'm so glad that you guys sort of stuck around, and I'll be meeting a few students, I believe. Ayusha set this up, and if there are sort of like requests for more meetings, just send me an email, and we can always chat outside of what I have time for today.
Sounds great.
Thank you very much.
Thank you.